and also Continuum Mechanics. Okay, this is a kind of derivative. So for understanding this kind of derivative, material derivative, you have to have a underlying field. Okay, that field may be scalar field or vector field. Let's say we have a field, underlying field, that is heat field. Okay, and actually this field depending upon spatial variable and temporal variable. Okay, so let's try to draw this constant edge curve like this, and actually this parabolic type curves, because we know heat equation always satisfy parabolic equation. Okay, through the region that is xy, we take 2D only. So now you were passing through this path, the region. So what will you experience in this path? And here is you, and this is your velocity component. Okay, p. So you actually experiencing that kind of heat distribution with time. Okay, heat, and this is heat actually experienced by you and any time. If you want to consider how much change in heat with respect to time in your path, this gives the tangent to the curve at any point, and this is denoted by dh dt following you. But here h does not represent that field. Okay, so dh dt that is following you. So according to partial derivative, let's give the change of heat field with time added with del x del h del t, as special variables are implicit functions of time. So by the chain rule of partial derivative, this gives this. Okay, we can define this is the velocity component of u in x direction, and this is velocity component of y direction. So del h del t is vx del h del x plus vy del h del y. And if you write just h apart from that, is vx del x plus vy del y, and here is h a field. So this also can be written as the time derivative plus this is your velocity component v. I write it as a vector dotted with the gradient, and this is gradient in 2D. Okay, this is an operator, and this acts upon the field h. Here h represents the field. In 3D we can write that same as del t by p. Here we will have the 3D component, and this is also 3D gradient, and ah is a field. So this actually operator denoted as caps D and operated on H, and this represent the rate of change of H with time following a particular particle, okay, as U. Also, this expression can be thought as another way. Let's see. We know always, okay, your velocity directed towards your path tangentially, but the change of h, that is heat field, heat, okay, is denoted as gradient of h, and this is direction. This direction will be, actually perpendicular to the constant h curves. Perpendicular to the constant h curves. In this point, actually, is directed towards this direction. Okay. So change along your direction. We are considering change of h, actually, change of h along your direction. How much it will change? The velocity component that is in your direction, and this is the change. Okay, dot. There is a dot. So the dot product of two vectors, that is your velocity vector and the change, the gradient of h, both of the vectors, and that can be written as velocity dotted with gradient of h. So anytime change the heat in your direction with time, that represented as dh dt following you, or for particle following that particle, and this h does not represent the field, equal to change along your direction, that is v dotted with grad h field, okay, plus you have to add the time dependent change of h, that is del t of h. Here h is a field. If you extract h, then you will get del t plus v dotted with grad, okay, which operates on h field, and this gives the same result as we previously defined as ddt. Okay, so material derivative of some field can be thought as, or can be defined as, ddt of h equal to del t, time dependent change, plus velocity vector with grad acts upon the field. Here the change of heat following a particular particle, following a particle, following a particle. Okay. This gives the material derivative